This video is about circular motion. It includes an example with a vertical circle and lots of examples with cars traveling in horizontal circles both on flat and banked roads. Please take a moment and read the success criteria we'll be covering in this video. Okay, so let's first think about swinging a ball at the end of a rope, and let's move it in a vertical circle. Now you know if you do this, you have to go fast enough for it to make a complete circle. If not, it never makes it to the top and just kind of falls down. So that means there's going to be a slowest speed possible in order for us to do this. In order for us to get this centripetal force, we have the weight pulling down at the top of the circle, and we just said for the minimum speed, I actually have no tension. At that speed, the weight will be just enough to cause the centripetal force to move it in the circle. Remember, the centripetal force is a net force, and something has to cause it. Now, when we get to the bottom, the tension is never going to be zero. Take a look at the free body diagram. At the bottom, tension is always going to be pulling it up, and now weight is in the opposite direction, pulling it down. In this case, it's going to be tension minus the weight that's going to cause my centripetal force towards the center of the circle. I'm always going to need to have tension being greater than the weight. Okay, so let's think about a car traveling around a corner on a horizontal dry surface. So if it's dry, let's say that mu equals around 0.7. That's a pretty good coefficient of friction for a dry surface. Now, let's think about some of the other values we could use. Let's say our radius of the circle is around 25 meters for the driving around a corner. And that means we're going to have, in this case, my centripetal force is only going to be caused by the force due to friction. Let's put in some values. Substituting this in, we know the centripetal force is mv squared over r, and my force of friction is going to be mu Fn, or the reaction force like we have in the data booklet. Now, since it's on a flat surface and we don't have any acceleration vertically, we know that the normal force is going to equal the force due to gravity. So on the right side here, I can write just mg. Notice my masses are going to cancel out. And if I rearrange this equation for v, I'm going to have v equals mu g r under the square root sign. And if I put the values into my calculator, I'm going to get 13 meters per second. But that doesn't mean much to me, so let's go ahead and put that into kilometers per hour because I am driving in a car. Now, 13 meters per second, and let me write it as fractions. I know that there's 1,000 meters in 1 kilometer and 3,600 seconds in an hour. Remember, we write it in this way so that the units cancel out, and now we're going to be left with kilometers per hour. And in this case, I get 47 kilometers per hour. That means on the dry surface with this radius, if I go faster than 47 kilometers per hour, the friction will not be strong enough to cause a centripetal force, and I will not make this corner. I will continue in a straight line and run off the road. Okay, so let's do the same thing as before, but now with a wet surface. How does that change our problem? Well, it'll mean we'll have less friction. So let's say now our coefficient of friction is only 0.4, and we use the same equation we derived in the last slide. And if I put in my new values, I'm going to get 9.9 meters per second, or that's the same as 36 kilometers per hour. Now, in other words, I have less friction and I'm going to have to slow down in order to make this corner. As I say in my class, as a Canadian, I definitely know that the winter time has much less friction and you definitely need to slow down on snow and ice. Okay, so let's do some more examples now. Let's think about having a banked corner. What that means is you can see my car is now on a slight angle as I go around the corner. It is traveling on the road out of the paper towards me. If you look, we have vertically no acceleration. That means the upward forces must balance the downward forces. So let's look closely at what those are. The reaction force, which I also call the normal force because it's always perpendicular to the surface, is acting in this direction here. So it now has a vertical and a horizontal component. Vertically, the component here is going to be n cos theta because my theta here is the same as this angle right here. So that means vertically, that component of the normal force is going to equal the force due to gravity, m times g. Now horizontally, we've got just the horizontal component of the normal force. That is the only one we have if we ignore friction for the moment. That means horizontally our force n sine theta is actually responsible for this centripetal force. So let's go and add in some of the values we've had from the previous example. So Fc mass times velocity squared over r is going to equal our normal force sine theta. Now we know from above here, vertically, I can rearrange that. So mv squared r, normal force, is also going to equal mg divided by cos theta, using our details from the vertical direction. And now we have, times theta. I almost missed it out. Our masses are going to cancel out. And if you remember the trigonometric ratio, sine theta over cos theta, well, that's the same as tan theta. And on the on the left, I have v squared over r. If I'm going to rearrange that, I'm going to get v equals the root of rg tan theta. And putting that into my calculator, I'm going to get 4.6 meters per second, or 17 kilometers per hour. Now, in this case, we've been just ignoring friction, and well, I call that math land in my class. It's not possible to have a perfect surface. But this does show that going around the corner when it's banked or on an angle means we could go a little bit faster because we're going to get help from the normal force. Here's where it's going to get a little tricky. Let's try this with some friction. And let's use a dry surface, so we're going to be back to mu equaling 0.7. Now look at the direction of my friction. It is along the surface of the road, and it's going to be part of the cause of the car making the corner. Now we have both a horizontal and a vertical component of the force of friction. In this case, we're going to have to break it down just like all the other variables. So we have here F horizontal is the force of friction cos theta, and the vertical component will be F sine theta. So let's write our centripetal force will be the normal force in the horizontal direction, and it's going to be the force of friction in the horizontal direction as well. Let's put some expressions inside. We have mv squared over r for the force of the centripetal force. We have Fn sine theta, which will be the horizontal component of our normal force. And I've also substituted mu Fn for our force of friction. And just to make this easier to read, I'm going to factor out Fn on the right side. Now this looks messy, but we do have some more information vertically because we know it's not accelerating in that direction. It only has centripetal force or centripetal acceleration towards the center. So that means my vertical components are going to have to be equal. Upwards I have the vertical component of the normal force, Fn cos theta, and downwards I have the force due to gravity plus the vertical component of the frictional force, mu Fn sine theta. Now to make this a little easier, I've moved the parts with Fn over to the left side. I'm going to factor it out and isolate it for Fn. We're almost there. All we have left to do is to take this new expression of Fn and put it back into our equation up here we had from the horizontal work. So all I've done is rewritten the vertical information in green and the horizontal in red. And I'm going to take my value of the normal force here and I'm going to substitute it in to the horizontal expression. So my masses are going to cancel out again. And I'm going to rearrange this for V. I know it looks messy, but this is as rough as it's going to get. Make sure you can also do the same algebra I've done. So if I put in the values of 9.81 for G, 25 meters for my radius, 5 degrees for the banking curve, and the friction of the pavement as being 0.7, I should get then all of these values 14.3 meters per second or 52 kilometers per hour. So let's look at all those values together. My car going around my flat, dry road, I could get up to 47 kilometers per hour without it coming off the road. If it was wet, then I had to slow down to still make the corner. And if I was on a banked corner at an angle of 5 degrees, I was able to go as fast as 17 kilometers per hour and not have any friction helping me and still make the corner. But realistically, if I had friction on my dry road, I could go even faster than all of the other examples together, and I could go 52 kilometers per hour and still stay on the track. Now, if you think about it the next time you're in a car, most of the on-ramps and off-ramps for highways actually have a slight bank. And if you want to go even faster, think of NASCARs or even velodromes for bicycles for the Olympics. They even travel faster, and they have a much greater banking angle, as it will allow the car or the bike to go around much faster at higher speeds and still maintaining the centripetal force needed to make the circle. Well, I hope after watching this video, you can now confidently say yes to all these success criteria. Please take a moment and read them again.